In this video, we're going to provide a brief introduction to running various statistical hypothesis tests in the RStudio environment. To begin, let's start with a two-means test with either equal or unequal variance. So suppose that you have two variables, one of which is binary and one is numeric, for example, birth sex and risk score, and you'd like to determine if there is a difference in the mean risk scores for the two different groups given by your binary variable. The t.test function in R will allow you to do so, but the way in which you enter it is a little bit unique. You start off with the numeric variable and then enter a tilde followed by the binary variable. And what this format is doing is it's saying we're trying to model risk score as a function of birth sex. It's called a model formula formulation. Now, we want our data to be taken from the student's 15 data set. If you have not uploaded that into RStudio, you'll need to do so before proceeding with these examples. And if we hit enter, notice that a t-test is performed for a difference in means. We are given the mean in the female group and the mean in the male group. And we have a very small p-value, which means in this case, of course, we would reject the null hypothesis and conclude that there is a significant difference in mean risk scores for males and females. Now, notice that in this output here, there are also several options listed. Here, the alternative here is two-sided, not equal to 0. Also, notice this Welch two-sample t-test option. That actually is assuming unequal variance. If you wanted to test to see if they do have equal variances first, recall earlier in the semester we discussed using the tapply function. Now, tapply, the way it works is you choose a specific variable, for example, risk score, and we choose a different splitting variable, which we would like to use to split the sample into groups, for example, birth sex, and then we put in a function, for example, SD, that we'd like to apply to both groups. So we can see in this case that males and females had roughly equal standard deviations for a risk score. So we may want to rerun our t-test using the variance equals true option. And notice in this case there was really very little difference in terms of the outcome of the test. In fact, the degrees of freedom even and the t-statistics were almost identical. The second type of test we're going to discuss is a two-proportion test, which you'll recall is used when comparing proportions for two different binary variables. So for example, let's suppose we wanted to know now if there was a difference in the proportion of males and the proportion of females who were low versus high risk takers. Well, in this case, what we could do initially is make something like a pivot table where we show the breakdown of risk level by birth sex. In R, the table command will do that for you. So we can see here that we have 26 female high risk takers versus 56 low, and it does look like for males there are more high than low risk takers. If we want to do a two proportion test, we simply apply the prop.test command to the table itself. Excuse me, my spelling is not always accurate. Prop.test, not prop.tests. And you can see here that it did a two-sample test for equality of proportions. And notice it does give us a p-value. Notice also, though, that it did actually give us a chi-squared value instead of the typical z statistic we usually work with. In R, instead of doing the z-test for equality of two proportions, it actually does a chi-squared test. The results end up being equivalent, and in this case you can see that we would reject the null and conclude that there is a difference in the proportion of males who are high risk versus females who are high risk. The next test is a more general chi-squared test. The chi-squared test can be done using the chi-square.test option in R. If you'd like to find out more about how that one works, you can help chi-squared.test. And notice here that the format is fairly similar to things that we did before. You enter a table and you can end up spitting out the results of the chi-squared test. So for example, we could actually do this just for our last example again here. And the results are the same, of course, as the two proportion test in this particular scenario, but you can now use more general categorical variables in performing this test. The final test I'd like to discuss is an ANOVA. For ANOVA, the function is AOV, and the format in which you enter things is fairly similar to what we did for the t.test function. So suppose you want to look at how risk score depends on something like class standing, which has more than two variables. If we run that in AOV, you see that we end up getting these results here, and it doesn't actually give us a p-value, but it does give us the sum of squares statistics we discussed in class. So if we want to figure out a actual p-value, we can go back to summary here, type summary at the beginning, and when you do summary in front of the AOV, it will actually give you a table similar to some of the ones we discussed in class. And in this case, we can see that the p-value is relatively large. Our F statistic is relatively small, which means that in this particular example, there's no evidence of a statistically significant difference in risk scores for different classes in the data set.